So, in the last lecture we showed that a large number of minor gases contribute to Earth's greenhouse effect. Although carbon dioxide, water vapor and methane are very important, there are many other gases which also contribute. Now, these gases are in parts per trillion, but since they remain in the atmosphere a long time, if you are trying to estimate the temperature change over the next 100 years, you have to take into account the role of these minor gases. So, how do you compare two different gases which may have the same amount of radiative forcing, but one gas remains in the atmosphere only for a short time, while the other one remains there for a long time. So, to do that, the Intergovernmental Panel on Climate Change came up with the concept of global warming potential, GWP. It is an index that describes the radiative forcing of well mixed gases that represent the combined effect of how long the gas remains in the atmosphere and how effective they are in absorbing the outgoing long wave radiation. Okay. So, this is where to compare different gases. Now, why do we need it? Because when you come to an international treaty to restrict the release of these gases into the atmosphere, we have to give priority. We have to give high priority to gases which absorb lots of radiation and are there on the Earth's atmosphere a long time, in comparison to those gases which may have a high radiative forcing, but remain there only for a few years. One example is methane. Methane has a typical lifetime of about 10 to 20 years, because methane ultimately oxidizes, becomes carbon dioxide and water vapor condenses, carbon dioxide will be there. On the other hand, if you look at chlorofluorocarbons, which we mentioned in the last lecture, they do not react much, they remain in the atmosphere for a long time, hundreds and thousands of years. So, although they may be in parts per trillion, although their present radiative effect is small, integrated over 100 years, they have a strong impact. Okay. So, global warming potential depends on two parameters: the ability of a given gas to trap heat, that is its radiative forcing, and the lifetime of the gas, how the gas decays over time. Okay. Now, for making life easy, IPCC decided to use CO2 as a reference gas. CO2 also decays in time with a very complex time scale. So, we decided that they will compare all gases with CO2. So, by definition, the GWP of CO2 is 1, because that is a reference gas. Okay. And all other gases are compared to CO2. For example, methane effect on absorbing Earth's radiation for a 100-year period is 27 to 30 times larger a kg of methane compared to kg of CO2. So, if you want to reduce 1 kg of CO2 to the atmosphere, you will have the same impact with methane by reducing much lower amount, because its global warming potential is much higher. Okay. That is, for every kg of methane you are reducing, we have to reduce every 24 kg of methane or 25 kg of methane reducing is equivalent to reducing 1 kg of CO2, because CO2 remains in the atmosphere for a much longer period. Okay. So, although methane is a much stronger absorber of radiation, its impact lasts only for 10 to 20 years. Okay. So, remember that methane has impact on ozone, and ozone also is a greenhouse gas. Now, nitrous oxide is 273 times as powerful as CO2 over a 100-year time scale. Okay. So, we have to worry about nitrous oxide emission, although its concentration is very small, its impact is much larger over a 100-year time period, because its lifetime is much larger. So, the formula for calculating global warming potential is the integral from 0 to the time horizon, maybe 50 years, 100 years or 20 years, of the radiative forcing of the given gas X and its variation in time with the radiative forcing of the reference gas AR, which is CO2, and the radiative forcing of CO2. Okay. So, you are taking a ratio of the total radiative forcing over a time period of the given gas, comparing it to radiating forcing of CO2 for the same time period. Okay. So, you are taking 1 kg of a given gas with 1 kg of CO2. Now, the person who was involved in the discussion about ozone depletion was a well-known scientist called Bert Berlin. Okay? And he is the one who proposed the setting up of the Intergovernmental Panel on Climate Change. Okay? So, IPCC came about during the time of the Montreal Protocol, which was agreed upon to reduce the depletion of ozone. At that time, he realized that it is very important also to have a similar protocol for carbon dioxide and other greenhouse gases. So, our attempt to control the impact of CO2 in the Earth's atmosphere is linked to a successful treaty for controlling the ozone depletion. So, IPCC created in 1988, and it was soon after the Montreal Protocol of 1987 to control ozone, and Bert Berlin felt that in order to convince the governments of the world to control CO2, there is a need for assessment of the scientific data and the assessment of the impact of carbon dioxide, so that you can form realistic response strategies. So, the world's attempt to control the ozone layer depletion by the Montreal Protocol was the precursor to the Kyoto Protocol, which was arrived at later. And it was during that time that IPCC was formed, which consisted of a representation of 194 countries who had to review the documents prepared by IPCC, and this document is reviewed by almost all the countries. And Paul Edwards, a historian, says that the IPCC draft report are the ones which has undergone more scrutiny than any other documents in the history of science. Okay? Because of the impact that controlling CO2 will have on our economy and our life, people examine these reports very closely to look for any mistakes in this report. So, what is important to remember that IPCC does not do science. IPCC merely assesses the literature that is already there, okay, and tells you what is known at that time. Okay. And based on that, the governments of the world have to make judgment. Now, IPCC evolved, created in 1988. The very first report was made in 1990, and in that report they admitted that they are not able to deduct unequivocally that the enhanced greenhouse effect due to carbon dioxide is on account of human impact. Okay. So, they said they are not sure. They said it may take maybe 10 years or more. Then 5 years later, a more complete report was published, where it was said that the balance of evidence suggests that there is an impact on global climate. Okay. Now, they were not very sure, but they were fairly certain something is happening. Then further 5 years later, they said most of the observed warming over the last 50 years is likely to have been due to increase in concentration. Okay. And the word likely is used very, very carefully by IPCC. I will talk about that. Likely means 66% chance that it caused by human beings. Okay. Then another 7 years later, the next report was more sure. It said very likely, which is 90%. Okay. So, you can see as the reports evolved and more data was collected and more papers were published, IPCC became more and more confident that human beings are altering the Earth's climate. Okay. Then in 2013, they said clearly that it is extremely likely that anthropogenic drivers cause the dominant observed warming since the mid 20th century. Extremely likely in the language of IPCC is 95% chance. Okay. They also said in 2021 that it's virtually certain that global upper ocean has warmed because of greenhouse effect. The chances that it is due to human being was 99%. So, 2021 clearly established that human beings were controlling the heat content of the ocean. Okay. So, I want to see how gradually we started from 1990 and slowly the certainty about global warming due to human beings was increasing to reach about 99%. Okay. So, this gradual increase shows the very cautious approach that IPCC took over this. And to show you how carefully it is done, typical IPCC report has around 200 authors and about 14,000 published papers are cited and assessed, and they get about 78,000 review comments which have to be addressed, and the response to the comments are available in the public domain. Okay. And in the final draft, which was read line by line, 40 countries commented on the final draft, the final draft that was made. Okay. So, it is a very carefully judged document. Okay. Now, the lifetimes of non-CO2 gases is dependent on photochemistry, okay, and how it is removed by various chemical reaction. When the lifetime of the gas is comparable to CO2, it is clear that removal of CO2 cannot be adequately described by single exponential lifetime. Okay. So, you have to worry about the lifetime of all the molecules which are contributing to greenhouse effect. Now, one of the problems is that what is the time horizon we choose to calculate greenhouse effect? Okay. Unfortunately, it depends on what impact you are studying. If you want to know how the climate change will change, global climate will change over the next 20 years, you have to use a 20-year time scale. But you want to know what is going to happen over the next 50 years, then you have to do a 50-year time scale. And if you want to know what is going to happen 100 years from now, in the next century, then you have to use 100 times. So, time scale that you are going to use depends completely on what particular issue you are addressing. Is it sea level rise? Is it heat waves? Is it floods? Depending on that, you have to choose your time scale, and depending on that, GW will change. So, this is what makes this a complicated issue. Okay. Now, if we look at the radiative forcing from 1750 to the present, you can see that the most dominant contributor is CO2, then comes methane, then comes nitrous oxide, then comes all those fluorocarbons called halocarbons. Due to the reduction of stratospheric ozone, of course, the negative forcing due to stratospheric ozone, but in the meantime, we increase the ozone that in the troposphere near the surface, that causes more greenhouse effect. Sulfate is an aerosol which causes cooling, so negative radiative effect. Fossil fuels, if they emit black carbon, they cause warming due to greenhouse effect. If they release organic carbon, they can reflect sun's radiation to aerosols, and that can cause cooling. And you have mineral dust, and you have aerosols like sulfate which cause cooling. We can have a role of contrails from aircraft. You can have the effect on aerosols on cirrus clouds. You can see the effect on land use. If you deforest the area of the forest, then you are changing the albedo of that area and causes cooling. And of course, due to effect of incoming solar radiation. But what I want you to appreciate is the solar radiation change is very small compared to greenhouse gases. Okay, play some role because of the 11-year solar cycle, but is nothing compared to CO2, methane, N2O, and halocarbons. You must remember that sulfate aerosol causes highest radiative forcing over land areas where they are very abundant. Okay, but also over water bodies, they have impact because water body has a low reflectivity, sulfate has high reflectivity. When sulfate appears on water body, it has a huge impact. Okay. So, the radiative forcing over land is much lower than over ocean, because ocean occupy more than 70% of the Earth's atmosphere. So, we compare the radiative forcing due to well mixed greenhouse gases like CO2, methane, and other gases, chlorofluorocarbons, with tropospheric ozone, which is going up at the surface, and the stratospheric ozone, which is being depleted. You can see that the dominant role is of greenhouse gases. There is some role of tropospheric ozone, but stratospheric ozone due to depletion has a negative impact. Okay. So, these are compared for a 5-year period in this IPCC report. So, you can see that ozone stratosphere contributes to negative radiative forcing, and then you have stratospheric ozone. Tropospheric ozone contributes to positive radiative forcing, because increasing, this is decreasing. Sulfate, because it reflects radiation, it causes negative forcing in the shortwave region. Then you have fossil fuels and organic carbon, fossil fuel and black carbon, and then you have black carbon alone from other sources, and you have volcanic eruptions, then solar radiation. Okay. Now, in all these things, you must look at their lifetime. You see clearly that methane and a halocarbon called HFC 134A have a very short lifetime, less than 50 years, while carbon tetrafluoride and SF6 have a long time. So, this has an impact on radiative forcing. So N2 and carbon dioxide also have a long lifetime of hundreds of years. So they are going to have an impact which is increasing in time because they are not removed easily by the atmosphere, while this one HFC 134A decays within 50 years, so it will go away from its impact on Earth's climate. Now, to understand this, imagine putting 1 gigaton of each gas at time t equals 0, just a pulse you throw in. Okay, you're throwing 1 gigaton of methane, within about 10 years the methane will disappear. While if you put 1 gigaton of CO2, it will remain in the atmosphere for a long time, almost 600 years or 700 years. So 1 ton of CO2 emitted today has much greater impact than 1 ton of sulfate aerosol. Now here is a comparison for 100-year period showing the perfluorotributalamine, which has a global warming potential of 7100 years over a 100-year period, so it has a long life scale. So this must be kept in mind. So here is a comparison in a table between the GWP of CO2, methane and so on for 20 years, 100 years and 500 years. Now because CO2 is a reference gas, by definition its GWP is 1 whatever the time horizon, okay, does not matter. But if you consider a 500-year time scale, then you find, so now we compare 100 years with 500 years, you see a huge difference here, okay, for SF6 for example. So depending on the application, normally people use 100 years, okay. 100 years is the typical time horizon in IPCC because they want to limit the global warming to around 2 degrees centigrade by 2100. Okay. But there are other applications like sea level rise where you may have to worry about 500 years. Now here is a comparison of GWP for different gases for 20 years, 50 years, 100 years, 200 years and 500 years. What I want you to notice is that if you consider only a 20-year period, methane is 35 times as powerful as carbon dioxide. But if you consider a 500-year period, methane is only 4 times more effective because methane is a small lifetime, so it will decay and go out. So its impact will not be as bad as CO2 over a long period. Now you look at gases such as CFC11, it has GWP of 4500 at 20 years and 4500 for 500 years is slowly decaying but not dramatically. But look at HCFC 123, it is 1.71 lifetime, and so in 20 years it has a strong impact, see that. But if you take 100 years, very small. So to me 500 years. So this shows the importance of what is the time horizon for your estimates. So this is shown graphically. Gases which have a long lifetime, their GWP goes on increasing with lifetime, okay. While gases which have a small lifetime like HCFC, that effect goes down with time horizon. So this is showing that gases with a small lifetime, the effect will start declining quite rapidly, while those are long time will go on increasing for a long time. And that is why GWP of gases which have a long lifetime goes on increasing. Okay. For example, if you took a 10-year horizon, you will say HCFC 225A is worse than N2O. But if you took a 100-year lifetime, you go opposite. So it's very sensitive to the lifetime of the gas, and this has to be kept in mind when you do calculation. Now here is another example where the radiative forcing is calculated. For gases with short lifetime, the radiative effect rapidly goes down, okay, per kg of gas, while for CO2 it slowly goes down. For C2F6, which has a lifetime of 10,000 years, it hardly changes. Okay? So these are things you must keep in mind when you read IPCC reports about global warming potential. The different values quoted, you should first check at the time horizon. Time horizon determines the value, and different tables contain different time horizons. So please be careful when you look at them. Okay? Now these calculations keep changing. If you look at the 1990 report and the 2000 report, there are some small differences in the CO2 equivalent that's calculated, and that's because as the time went along, the calculation of GWP became more and more sophisticated. For example, take methane. Methane calculation initially was done rather simple way. They didn't take into the fact that methane becomes CO2, that CO2 will continue to be there in the atmosphere for a long time. Okay? Although water vapor may condense out because of the temperature of that layer, but methane will have a long term impact because methane ultimately produces carbon dioxide when it reacts with oxygen. Now these are the GWPs compared to CO2 given in various tables of, and I'm showing you how they change from the second to fourth to fifth. Okay, numbers are changing. Okay, because better data is obtained about lifetime, better data is obtained about radiative forcing. So IPCC continues to try to make its estimate more accurate. So the data will change in time. So always use the latest IPCC report to look at these numbers, because numbers are evolving in time. So you cannot ignore those facts. Okay. Now you know that all these data for radiative forcing obtained based on radiative transfer models. Okay, and so you have to be very careful which model data you are using, because numbers will change according to the model used. Okay. Now you must also remember that the effect of a gas in the troposphere is different from stratosphere because the lapse rate is different. That is, temperature decreases the height from surface to tropopause, but it increases with height in the stratosphere because of the ozone layer. So this changes the way greenhouse effect operates in the troposphere and stratosphere, and this must be clearly understood to avoid any confusion. So for example, take ozone. Ozone, when it occurs in the stratosphere, if it increases, it will reduce greenhouse effect. Well, the same ozone in the troposphere will increase greenhouse effect because troposphere temperature is falling with height. Here temperature increasing with height. So this point must be understood, and so I am going to talk about it, but I will reserve this for the next lecture, in which I will talk more about the role of temperature variation with height on the greenhouse effect.